Hello, everybody. Thank you for joining us today. We are part of the over 400 people worldwide who have registered to this webcast on Wafer for more than more application. This webcast is presented by Yole Development and with the participation of SPTS and Corning. My name is David Jordan, and I am Global Support Sales Coordinator for Yole Development. So before we get started, let me give you some practical information about the webcast. You will have the opportunity during the whole webcast to submit questions. To do so, you simply have to use the box at the bottom of the screen labeled Ask a Question. We will answer as many questions today as time permits, and for remaining questions, we will follow up by email with all the participants. So concerning the material and webcast contents, please note that the presentation is available and downloadable in the resources section. You will also receive an email after the webcast within 24 hours with a link to the full recorded audio sessions and video sessions. So today, Yole Development, SPTS, and Corning will share their analysis with you on Wafer starts for more than more application. So first, let's start with an introduction on the recent market forecast of wafer starts for all modern more devices, as well as wafer size and material trends presented by Amandine Pizzagalli. So Amandine is a technology and market analyst at Yole Development, and she specializes in equipment and material for semiconductor manufacturing. Amandine, it's up to you.
Thank you, David, for the introduction. Welcome, everyone, and thank you for attending this webinar on the wafer starts for more and more devices. My name is Amandine Pizzagalli, and I'm going to give an overview of the wafer starts market for more and more devices, with a specific focus on MEMS devices, radio frequency devices, CMOS image sensors, as well as power devices. So the slides I'm going to present are extracted from the report Wafer starts for more and more devices released in spring of this year. But before going through the presentation, so I would like to explain you our motivations behind this report. So this report was actually requested by various companies with different business models in the field of semiconductor, from IDMs to foundries for equipment and material suppliers, that needed forecast numbers related to wafer starts across the more and more markets. And after assessing this demand, so we realized that a synthesis of data we already have was missing, and we decided to build this report, which is actually a new type of Yole report, gathering the entire wafer starts market for more and more devices. So basically, the goal of this report was really to identify the key drivers that would shape the more and more industry. It gives detailed analysis and wafer forecast for each more and more application segment, and evaluation market development in terms of market size, volume, substrate size by more and more devices. So why more and more, and what drivers pushed the development of more and more? So as you know, in the semiconductor field, so there is a strong trend toward miniaturization, driven by smartphones, tablets, PC, TVs, and wearables, pushing the industry to develop devices with more functionalities packed into a smaller form factor. So transistor scaling and cost reduction will not historical trends beyond the 200 or 22 nanometer silicon nodes, and the design and manufacturing costs for transistor fabrication as such advanced nodes has increased substantially. So in order to follow the semiconductor technology roadmap to, let's say, bridge the gap between cost and performances, the industry is looking for technology solutions integrated at the same time, more functionality for integration. So more and more devices represent this new functional diversification, technologies combining performance, integration, and cost not limited to the CMOS scaling. and they are becoming more and more important. So given the short time we have today, I'm going to give an overview of the wafer starts market for MEMS and sensors, CMOS image sensors, power devices, and RF devices. So the key question to wonder is, what are the key drivers in terms of applications of these more and more technologies? So there are numerous megatrends, market drivers that contribute to the more and more devices growth. First of all, you have the 5G with the wireless infrastructure and mobile, bringing any service to any user anywhere. You have the mobile with additional functionalities, the voice processing, the smart automotive and electrification, and the augmented reality, virtual reality, finally, the artificial intelligence. So the next slide is showing the overall wafer demand, including MEMS and sensors, CMOS image sensors, power, and RF devices from 2017 to 2023. And actually, the wafer demand reached almost 45 million 8-inch equivalent wafers in 2017, and it's expected to reach more than 65 million 8-inch equivalent wafers by 2023. So first of all, if we take the example of power, so the power devices wafer market will grow at almost 13% growth. And in 2017, it stood for more than 60% of the overall more and more wafer starts, and it will continue dominating the more and more industry because it's basically driven by the increasing deployment of energy sources, industrial motor drives, growing also electric and hybrid vehicles. Then you have the 5G. 5G is a hot topic today, and it's likely to be a huge part of the more and more evolution, also requiring new antennas along with filtering functionality. And these new requirements will lead to increasing demand for RF components like RF filters, power amplifiers, low noise amplifiers to really ensure access to tomorrow's radio network. Meanwhile, there is a growing demand also for advanced mobile applications that integrate more functionalities, and that will require aggregating more and more devices like fingerprint sensors, under light sensors, 3D sensing, microphones, and inertial MEMS devices. And this will contribute to strong wafer growth in the MEMS and sensors wafer market. Then you have the automotive segment, and the automotive is a great driver of more and more devices. You have a lot of companies willing to extend their capabilities, for example, in ADAS and autonomous driving. And recently, so the leading company on Semiconductor acquired Sensing Technologies, leader in SPAD and leader sensing products for automotive. So we really expect smart automobiles to drive a consistent growth of CMOS image sensors over the next 5 years. Although most of smart automotive will be supported by these growth areas, you see a standard of classical MEMS and sensors like MEMS pressure sensors, inertial MEMS, that will continue growing at a reasonable rate, supporting the standard auto industry. The next slide is showing the wafer demand for more and more applications, but this time breakdown by wafer size. And in terms of wafer size, so the more and more wafer market, so including MEMS, CMOS image sensors, power with MOSFET, IGBT, thyristor, and diodes, excluding power ICs, with also RF devices, is today dominated by the 6-inch wafer format, which represents more than 35% of total consumption in 2017. It's followed also by the 8-inch size, which is mostly supported by power device applications. So basically, both 6-inch and 8-inch are forecast to represent more than 60% of the total wafer consumption of the more and more wafer. And even if the 6-inch will continue increasing over the next few years, its share will begin decreasing compared to the 8-inch wafer format, we expect 8-inch wafer to progress significantly and surpassing 6-inch by 2023. So this transition basically will be driven by power and maintenance sensors application, where the vast majority will convert their components from 6-inch to 8-inch over the next 5 years due to increasing volume production. Then today you have also the 5G advancements, and it's taking place on 200 millimeters and 150 millimeters wafer technologies. You have also MEMS devices and RF technologies processed on multiple wafer size, and they have all increased in volume as a consequence of the advancement in the smartphone. In addition, so you have the 300 millimeter wafer size, which represents the fastest growth from 2017 to 2023, with a 15% growth. You have advancements in smartphone technologies based on the 3D stack BSI and hybrid BSI, and they have given rise to an increase in CMOS image sensors manufacturing on 300 millimeters. On the other side, so you have the 4-inch wafer, which is in large demand today for more and more applications, mainly driven by RF source filter products. However, the 4-inch adoption will decrease due to the transition from 4-inch to 6-inch for these applications. But we still see some more and more products manufactured in wafer sizes below 4-inch, like 3-inch or 2-inch wafer format. And this represents a very small volume, so we expect such sizes to die out aside from small volumes still used for producing MEMS, power, and RF filters devices. So here is an overview of the wafer start market data split by wafer size for 12-inch, 8-inch, 6-inch. So basically, we did a more in-depth analysis for every wafer size breakdown by more and more device. So it was just to give you a better understanding on the key applications or key more and more devices driving the 12-inch, 8-inch, 6-inch, and below 4-inch wafer formats. So technically speaking, you have a wide range of semiconductor material substrates that could be used for more and more manufacturing, like the glass substrate, SOI, SiC, gallium nitride, gallium arsenide, sapphire, ceramic wafer. So various substrate types besides the silicon substrate that could be used for manufacturing some more and more devices. And as you can notice, so a wide range of semiconductor substrate types could be used for some more and more devices, especially for RF devices and power devices, so it's quite broad and diversified. But the choice of semiconductor material really depends on the applications and the technical specifications required in terms of thermal conductivity, dielectric constant, mobility, but not only because it's much more complex, and it depends also on the technology maturity and device availability. So if we compare briefly the key parameters or features of the different substrate types available on the semiconductor market, you have, for example, the gallium arsenide, which exhibits the highest RF mobility. It has high breakdown voltage, low RF loss, but it has poor thermal conductivity. The silicon, which is the mainstream semiconductor material, it has low resistivity, so you have some limitation for RF devices, and it cannot compete at the high frequency range. For example, the glass material has low dielectric loss and low insertion loss. However, the glass has very bad heat conductivity, and it's not compatible for some RF components like the power amplifier, low noise amplifier, or some RF switches devices. So to summarize, I mean, the silicon material is mostly used for some applications that needs compatibility with a CMOS process. The gallium nitride, for example, is interesting as a high electromobility material for high-frequency switching. Silicon carbide will stay the preferred choice for high-temperature applications. In the case of glass materials, so it's a good option for low-power consumer like RFID and high-frequency applications. And you have the SOI, which is basically used for high resistivity applications. So here we see the breakdown by semiconductor material substrate, split by substrate type in terms of wafer volume for 2017. So regarding the semiconductor material type, of course, the silicon is by far the most dominant material used with more than 80% of market share. But you see alternative non-silicon-based substrates like silicon germanium, gallium arsenide, gallium nitride, and SiC, and this type of materials are increasing their importance within the more and more industry. So as I mentioned, silicon cannot compete in a high-frequency range RF application due to its limitations in terms of insertion loss and dielectric constant. And we are seeing now new technologies like silicon carbide or gallium nitride for high-power application for like electric vehicles. Both gallium nitride on SiC, gallium nitride on silicon are also very good candidates for RF power devices, especially for micro base stations. The gallium arsenide, so thanks to its, let's say, maturity on the market and satisfying out power and also good linearity. So the gallium arsenide is being used for power amplifier devices. And also it's a good material, good solution for small cell implementation for both sub-6 GHz and the first millimeter wave also applications. And meanwhile, so you have the silicon, germanium, and ceramic and SOI, which are the dominant technologies for low noise amplifier, RF BAW filters, and RF switches respectively. But let's say choosing the right substrate technology will strongly depend on the technological performance associated with the megatrends requirements as well as the costs. So to conclude, the wafer demand, including MEMS and sensors, CMOS image sensors, power, and RF devices for more and more, is expected to reach more than 65 million 8-inch equivalent wafers by 2023, with an almost 10% growth from 2017 to 2023. In terms of wafer size, so the more and more wafer market is today dominated by the 6-inch wafer, mostly supported by power device applications. Although 6-inch will continue increasing over the next few years, its share will decrease compared to the 8-inch wafer format. And the transition is really driven by power and MEMS and sensor applications. So as mentioned previously, also we still see some more and more products manufactured on sub-4-inch wafer format, but we expect such sizes to rapidly disappear, aside from small volumes still used for some power devices and RF devices production. The 300 millimeters will represent the fastest growth for 2017 to 2023, and it's mainly mostly driven by BSI, CMOS image sensors with the technologies 3D stack BSI and 3D hybrid BSI. And in terms of semiconductor substrate material, so even if the silicon is the dominant material used today in the field of semiconductor and more and more industry, you see alternative non-silicon based substrates, especially compound semiconductor, gaining some market share within the more and more industry. So thank you for your attention. And I have one additional comment. So I couldn't have done this report without the valuable input from Claire Trodek, Cédric Malacan, Eric Minier, Alexis Dibray, Pierre Cambou, Angeline and Hannah Villamor, who are responsible at Yole for market forecast in each of the more and more devices I covered today. And so I would like to take this opportunity to thank all of them for their contribution for this report. Thank you. And now I give the floor to David.
Thank you very much, Amandine, for this great introduction. Once again, do not hesitate to ask questions at any time using the Q&A button. And we'll have a Q&A session at the end of the webcast. Now let's continue with the analysis on trends in wafer processing technologies for RF MEMS. This presentation will be done by David Butler, Executive Vice President and General Manager at SPTS Technologies. David, it is over to you.
Thank you very much. Thank you for the invitation from Yole to talk to you today. This is probably the fastest moving technology that we're working in at the moment, and it's one of my favorite things to talk about. What we're talking about today is RF MEMS, and in particular bulk acoustic wave, BAW filters. This is a silicon technology. This is on 6-inch wafers, but quickly going to 8-inch. Bulk acoustic wave filters first appeared in mobile phones around 2005 when the 3G came along, and they're now the accepted way of filtering high frequency signals. Last year, something like 8 billion BAW filters were shipped. Now, the heart of these filters is a piezoelectric resonator, which is made by sputtering, by PVD of aluminum nitride. It's an aluminum nitride film. Last year, for the first time, scandium-doped aluminum nitride films appeared, and those increase the coupling coefficient of the filter, meaning really that it improves the performance in converting the RF into an electrical signal. And of course, if you get a bigger signal response, then that's a longer battery life. And now, almost over the last 12 months, scandium-doped aluminum nitride films are now in high volume. The addition of scandium brings its own challenges for us as a maker of PVD equipment. The coupling coefficient depends on the stress of the actual film. So you need near perfect stress across the whole film. As I said before, it's going into 8-inch. So you need near perfect stress control over the whole 8-inch wafer. Now I'll talk a bit more about processing in a couple of slides, but I just wanted to touch on the market itself and why bulk acoustic wave filters or BAW filters are so important. Now, some of you, most of you, have an iPhone. An iPhone is a world phone, meaning that you can go anywhere in the world, and the chances are you can make a phone call, whether that be in 4G going 5G, like in, I don't know, China, Singapore, or whether that be in South Africa, where maybe 2G is still the main frequency that is used. So your smartphone is going to be able to deal with all of those RF bands. Different countries have different carriers, and they have their own preferred frequency band. In the US, they have their own preferred frequency bands. And your phone is going to be able to deal with those different preferences, those different country rules, without dropping a line, without spilling over into the frequency bands used by the emergency services. And in a modern smartphone, there could be anything up to 40 or 50 BAW filters to deal with all these frequency requirements. And when 5G comes along, it's going to double to more than 100. So the market is exploding. We have a great position in aluminum nitride for BAW. We've worked with it since 1998. Our market share, we think, in terms of shipments of PVD systems, we have about 50% market share. We have more customers than any other vendor. It's grown since the early requirement for BAW. It's now appearing as a new MEMS material to replace silicon-based MEMS. Because it generates its own signal, it's a very low power consumption sensor. So, for instance, microphones are appearing now. There is Vesper is the best-known supplier of microphones built with piezoelectric aluminum nitride. They are appearing as some Alexa-enabled equipment, also fingerprint sensors. Companies like Chirp and InventSense are the best-known suppliers of those using this same material. So let's go and talk back to the technology. Now, I said earlier on that the challenge is you need near perfect stress control. But it's not only that, because the frequency of the filter is defined by its thickness. So you need near perfect stress control over the whole wafer, but you also need near perfect thickness control. And getting those two things at the same time is very difficult. If you look at this cartoon on the right of the slide, it's a simple depiction of a sputter tool. You have a target at the top made out of aluminium. You have a magnetron running behind the target to increase the density, to increase the sputter rate of the target. And the arrival rate of the material, this sort of target and magnetron will give you good thickness uniformity. By working with the geometry of the chamber, the target to wafer spacing, you can get extremely good uniformity at the wafer. For us, we can get better than 0.5%, 1 sigma on an 8-inch wafer. But that is not the same as stress control. The arrival rate of flux at the wafer is non-uniform. Ions arrive at the wafer at different rates. And when you apply bias, which is a primary degree of stress control, you attract flux to some areas more than other. Typically, you attract high-density flux at the edge of the wafer. That bombardment produces a compressive film. And if you see down here in the bottom left, this is the stress uniformity you might get in a chamber like that. A peak compressive stress in the middle, and a peak tensile stress in the center of the wafer, and then I've lost my graph. We're back, sorry about that. And a compressive film at the edge of the wafer. That stress range of around 300 megapascal max minus min is not a uniform stress. You may have uniform thickness, you don't have uniform stress. How do you fix that? First, you talk about thickness control. What we do to control about thickness control, we have a number of features in our system. We have magnetron adjustment, positional adjustment of the magnetron behind the target. We have a rotating platen, which can remove radially non-uniform patterns. But one thing we have is called the Bmax. This is unique to us. Now, as I said before, we use RF bias to give a stress value. As we already said, at the wafer edge, you get high density, and when you apply bias, you get increased sputtering at the edge of the film, and the film actually gets thinner locally. We have Bmax hardware, and this hardware opposes the arrival rate of these ions and stops the edge getting thinner. So you can see on this graph down here, without Bmax, it's edge thin because the edge is being locally sputtered, but with the Bmax, it's very flat. Uniformity better than 0.5%, 1 sigma on an 8-inch wafer. That's great. So we have thickness control, very uniform thickness. Stress control is different. For stress control, we have some new hardware called the crossbow platen. The crossbow works in the compressive and in the tensile range. You can see on here, we have the mean stress of the film was 550 megapascal or minus 250 megapascal compressive, but in both cases, we have a stress range of around 100 megapascal across an 8-inch wafer. This is something like 2 times better than our nearest competitor. And at the same time, we have thickness control. The thickness uniformity has not been affected. 0.5%, 1 sigma on an 8-inch wafer. This one here, the next one, is for a 8% scandium doped film. This is pretty much near leading edge for scandium doping at the moment. This particular example, we have a full range of 50 megapascal, full range stress control across the wafer, 200 millimeter wafer. That is about 4 times better than our nearest competitor. That is almost at the measurement limit of stress gauges. It's an invention that is not limited by the scandium content of the target. It's an invention that will work for the full target life. And coupling data provided by customers shows that the theory is correct. The stress control mechanism translates into very tight coupling coefficient over the entire wafer surface. So my summary slide then, so aluminum nitride has been in volume production since for 13 years now. They are in every smartphone. They increase every time the wave bands expand. 5G is going to be pushing layers to go thinner, and we're introducing scandium content into those layers. We are the leaders in aluminum nitride. We've been doing it for more than 20 years. Getting stress control and thickness control is the key challenge, and we are the only company who can provide that at the same time. Stress uniformity is far better than any of the competition. Okay, thank you very much for listening.
Thank you very much, David, for this interesting presentation. Now we'll have Raj Parmar, new product development manager for Corning Precision Glass Solutions. He will now provide an overview on the benefits of through glass vias for RF applications. Raj?
Yes, thank you, David. Hello, everyone. Thank you to Yole for the invitation. I'll spend the next few minutes wrapping up some of the things that you've heard already. Some of the themes that Amandine already touched upon, David just touched upon, how the RF world is rapidly headed towards 5G, and what that construes towards the components that make up the individual implementations that are happening in the wireless industry. Why we at Corning are excited about glass as a material and how it may impact both performance and packaging benefits. There are, within the wireless segment, there are multiple areas that could gain these benefits and that we could hold impact on, such as fixed wireless, base stations, maybe even automotive and IoT. But I'll spend the next few minutes taking a deeper dive into what we're observing, market inputs that we're getting from the handset world. And as I'm sure everyone knows, that's one of the most challenging areas, challenging markets, because the components to be used have to follow very aggressive cost curves, as well as size, footprint, including the Z dimension, and ultimately have to be the most succinct solution. So it'll be illustrative of what other markets can also start using from handset world. So the drive for 5G is largely in progress now, because the carriers, after all, want to build the fat pipe. There are techniques that are being used already today that take the networks into higher capacity, higher data rates, such as carrier aggregation, massive MIMO. So here's a summary of what the goals for 5G are. But on the bottom right, we illustrate that it all may come at a cost, and namely that's in terms of loss. So if we look at RF front ends, which are the components that stand between the antenna to the transceiver or the radio, all of those components are becoming more and more numerous as we head, and as David previously mentioned, about including more and more bands into this world smartphone that you have. And you see here that there's a trend towards higher and higher insertion losses, which cause greater and greater battery drain. And that all has to be mitigated with the inclusion of these new bands. So hopefully we can come up with material choices and technological choices and circuit topologies that all curb that trend. Otherwise, that would be a problem for consumer devices. So if we take a deeper look, and again, this is a simplified view of the trends that are happening, at least at the circuit level, and we see on the left that the 4G standards were implemented largely by using modules, and the modules may contain the power amplifier, the filters, the BAW filters that David was mentioning, switches, and so on. So in the 4G case, you were able to, with the number of bands, you were able to serve that with based largely two such modules, so subdivided into, we might think of it as high band and low band. And as we head towards including like the upwards of 43 bands, that is now broadening into much more complex implementations, which then lead towards upwards of 4 such modules, so high band, low band, and maybe ultra high band and ultra low band. Those also need to coexist. So as David was saying, you don't want to spill the spectrum into the neighboring one. LTE frequencies have to coexist with Wi-Fi. And as an example, we have these elements that are highlighted in green here as a different class of filters than what acoustic filters are serving. Acoustic filters are made for steeper edges and for narrowband, and this class of filters is largely implemented using lumped element or LC-based filters, so inductors and capacitors. And if we were to make a technological choice, we would want the best performance in class so as not to create more losses. So we feel that glass, as you'll see in a bit, is definitely the best candidate as we head towards being able to create these elements with the lowest losses and the lowest form factors. So at each of these component levels, we feel that there are either performance and or packaging benefits, and the ultimate end goal for the RF designers is to create a single substrate or a single implementation that includes all these various evolving frequencies into one succinct package and one succinct module. And for that, we would have to enable 3D packaging and interposers as on being originally showed on one of the charts. So we think that glass holds the potential of being able to merge all the way to RF interposers. So here's the technology. This device on the left is a 3D solenoid-based inductor. We juxtapose that with a thin film capacitor, and this creates the basis or the toolbox for these class of broadband filters, which could be implemented as diplexers, n-plexers, or as bandpass filters. And what we're seeing is that a true 3D approach and an element which has the lowest losses, so the best conductivity and the lowest capacitive losses, results in the highest Q. So Q is the measure of that quantity, and we see that over the incumbent technologies, things like LTCC and high resistivity silicon, that over the sub-6 gigahertz frequencies, the true glass-based or true glass via-based elements hold the highest performance. So that would lead to thinner, smaller implementations and certainly lowest loss or lowest current drain. A second component, which is in progress of making use of glass, both for performance benefits as well as packaging, is the RF switch area. So this has been, over the last few years, the domain of SOI, silicon on insulator. And what we see here is that there's an example of an RF switch which is MEMS-based. And MEMS as a process usually requires environmental stability, so hermeticity is of value. So this is where a glass encapsulation is one of the first steps that you would take at realizing the product. But the product itself is actually a system in a package. It needs actuation, ASICs, and other elements. And as a result, it's already a 3D structure. And for that, you would want the smallest form factor. So hence the holes that support the cap and the substrate. And what we see here is that it's also very broadband. So this particular switch has been characterized and compared to other technologies. Glass-based implementation shows far lower loss over a wide range of frequencies. So this would also be a very valuable element as we head towards the millimeter wave frequencies, which are getting into 28, 39 gigahertz. A third element, which is in progress also, are millimeter wave front ends. And what we're showing here on the left are a couple of different concepts that have been published in the industry, make use of existing materials such as organics and LTCC. Glass, by contrast, also has a very attractive loss tangent. So as the designers now take a look at how to marry the front end or the radio IC along with the antenna, which is going to be crucial because of losses and matching and flexibility of design and placement, we're seeing a huge interest now in glass-based approaches or potentially a hybrid approach to being able to do the 5G or millimeter wave antenna. So I'll just touch on one such example. We've worked with a partner company who has recently done some modeling of a patch array, which has been compared a glass-based implementation to an organic. And what you see is that there are gains available on the radiation efficiency. So these elements need to be omnidirectional. They're very short range. So of course, every last bit helps. And this is characterized over the 60 gigahertz frequency range at this point, but also shows benefits over other incumbent materials regarding efficiency. So in summation, Corning is investing quite a lot on glass, both from compositional standpoint as well as producing the through glass vias. We think that there are very attractive markets within the RF world that could be served, where glass has both performance and packaging and size and overall cost benefits. We think the lower losses can certainly be used in consumer applications where battery life is a key. We think that we can impact at the component level as well as at the module and at the system level. And our process approaches are creating very high accuracy elements and giving an order of flexibility with regard to the composition itself, as well as thickness and height choices for the system designers. So that's all I have. Thanks.
Thank you, Reg, and thank you all for your relevant presentation. We will now wrap up with a Q&A session. During this session, we will answer as many questions as time permits, and we will follow up the email for the remaining ones, and we already answered some through the platform. So you may also still carry on to ask questions during the Q&A session. We have seen that there was a technical problem and some do not have the presentation in the resources section. So we will send an email to all participants with the PDF attachment. So first question is for Emily. Emily, we got a questions, which is, what are the applications driving the 6-inch and below 6-inch wafer size?
So below 6-inch, so yeah, you have some mentioned sensor devices. They are still produced on sub-4-inch wafer, so it's mainly for high-end applications like defense and space. You have also filters. So actually, they are the largest market among RF components for mobile handsets. And today, they are mostly produced on 4-inch ceramic-based wafer. And these components will see probably strong growth in the next several years. And I guess also the last main device also produced on 4-inch is the RF gallium nitride on SiC. So it's mainly used for base station and defense.
All right, thank you. Another question. Are there any emerging CMOS image sensor products, and what are the relevant wafer size for those?
So I guess for the emerging CMOS image sensors product, so you have the image sensor to enable full phase difference autofocus pixels. You have image sensors for advanced driver assistance systems. So I guess the PDAF will be based on 12-inch, and everything related to automotive is still based on 8-inch. So you have seen also recently, I mean, since 2017, so Sony provides triple stack sensors running into production for super slow motion for high-speed shooting. So it's mainly based on 12-inch wafer. And you have new CMOS image sensor approaches like global shutter and time-of-flight technologies, probably based also on 12-inch wafer format. And then the 3D sensing using time-of-flight sensors.
And the last question for Amandine. What are the key applications for gallium nitride, and what are the trends also for the wafer size?
So depends. So you have two types of gallium nitride. So I'm not the expert of compound semiconductor, but you have the gallium nitride on SiC, and this type of material is mainly used for RF devices for power amplifier, for wireless infrastructure. So for the following market segments like space, defense, military related. And you have the other one, so the gallium nitride based on silicon. Basically used for power applications like for power supplies or automotive or commercial telecom and community antenna television. And basically this kind of substrate for this application are based on 4-inch wafer size.
Great, thanks. We also have one question. Well, we have a lot of questions, but we will answer one for David. David, the question for you is it true that the better the texture, the higher the coupling coefficient?
Okay, yeah, I mean, that's a good question. Texture, just for those people who don't familiar with it, texture is a word that basically means the crystal structure of the film. How well aligned the crystals are in the growing film. And yes, if the structure is, or if the texture is worse than 2.5 degrees, now here's another phrase people don't understand maybe. When you do an XRD measurement of the film, a tight structure shows as a very tall, thin line, a very strong response at a very narrow wavelength. And if you measure that response, that gives you the full width half max, which is measured in degrees. If the film is worse than 2.5 degrees, so it's a fairly flat structure, not a very strong response, it doesn't behave as a piezoelectric film. It doesn't work. If it's less than 2.5, it gets better. And frankly, if it gets to around 2 degrees, slightly better than 2 degrees, the piezo is probably as good as it's going to get. Try and improve it further by process techniques, underlayers, smoothing stuff you can do. You can do it, but it's really wasted effort. The return on investment of going to much better than 2 degrees doesn't really improve the coupling a corresponding amount, and your time is better off spent on stress control, thickness control, things like that. But anyway, back to the question. Yes, better the texture, the higher the coupling coefficient, but it doesn't keep going. It doesn't keep getting better forever.
Thanks a lot, David.
Okay.
Now we'll end with one question for Raj. Raj,
yes.
When do you see 5G micromillimeter wave entering mobile markets and mobile handsets?
Yes. So regarding 5G, the sub-6 gigahertz frequencies that we were describing and touching upon earlier is already under progress. So handsets and the networks are in process of doing some of the first deployments. As far as the millimeter wave, we've talked to customers who plan for at least some low volume at the second half of 2019, heading into 2020. So that's about our best estimate directly from markets we serve and customers we serve as to what the planned rollout is.
Okay, thank you very much, Reg. Now, unfortunately, the webcast is over and we'll have to end it. So just a few practical information before we leave. You will get within the next 24 hours an email from the platform that will give you a link to the recorded session of this webcast. Also, feel free to share the presentation that we will send you by email to any colleagues that could benefit from this presented material. And also a quick reminder, you can find all our analysis and reports on our web portal, imicronews.com. So do not hesitate to contact us also if you have additional questions. You can find appropriate contact in the different slides. Thank you all of you for joining us today and have a good end of day. Bye-bye.